Hey everyone, this will be our lecture today instead of me trying to do this during class. So hopefully this will be helpful as you get ready to finish up this unit on circuits. Just a couple of things to think about. You will have to take your first LO on Thursday. Right in a moment, I'm going to introduce some upcoming token opportunities. If you complete these, you would get an extra retake or a retake past the deadline for the learning objective of your choice. You only get one retake for each token. I made assignments that are found on our Canvas page that you could turn in your materials that you needed to do to show that you attended those token opportunities. And here they are. The first one is this week. There's going to be a movie night in McPhail's. I think that's Thursday at 5 p.m. So if you attend that and watch the movie, which is a very good movie, and you could grab some pizza. You can see your instructions on the assignment for this under the Canvas page. There's also an opportunity after break where in celebration of Pi Day, which actually does occur during break, so we're going to be doing it a few days later, you can actually pie your professors. Some of the STEM professors will be available to have whipped cream pies put in their faces, and if you attend this, you could also get a token. All right, so the things that I'm going to be doing today are going to be the last part of the first learning objective, which is Kirchhoff's rules. And this is for more complicated circuits that we can't just use our rules about things connected in series and parallel. And then finally, we're going to look at RC circuits. Just a quick review of things we've done so far. Really important expressions that we should be remembering is Ohm's law that makes a relationship between voltage, current, and resistance. And then also the different expressions for power, whether it be the power generated by a battery or that lost in a resistor. Also, as a review, what happens if we want to simplify a circuit of resistors in series? We simply add the resistors to find the equivalent resistance. Both of these resistors have the same current, but they have a different potential difference. For resistors in parallel, they both have the same potential difference across them, but they have different currents running through them. In order to simplify them into a single resistor, we add the reciprocals of the resistances, and this gives us the resistance of the equivalent. But sometimes you're going to be confronted by a circuit that you just can't figure out how to break it down into simply parallel and series. Here are some examples of circuits. Sometimes they have two batteries and that gets confusing. Or the one on the left is just, there's some parallel and series and it's pretty confusing. So we use what we call Kirchhoff's loop rules. There's two basic rules that we want to use. One has to do with how the currents in different branches relate to each other, and we call it the junction rule. If you remember, I've already pointed out that a junction is a point where the current can split into different paths, or where the current can come together from different paths into a single path. The junction rule is presented as the sum of the currents is zero, but this actually means currents in to the junction minus currents out equals 0. So currents coming out are treated as negative. Currents coming in are treated as positive. For this picture, we would have I1, which is coming in, minus I2 minus I3 equals 0. Here's a picture where we could do a junction rule. And at first, you might think that, oh, I have two junctions, so I can do it twice. But you should actually notice that if we do it for this junction and this one, we're going to get the same expression. For instance, up here we have I3 and I1. So coming in, I would have I1 minus I2 minus I3 equals 0. And now if I go down here, I get I2 plus I3 minus I1 equals 0. These are actually the same thing. If I put the negatives over to the other side, this becomes I1 equals I2 plus I3. And this one does as well. So if a junction involves all the same same currents, if you have more than one junction, you're probably not going to get a unique expression from both of those junction points. This is also, to me, a preferred way to think about the junction rule, where I like to think of the current in is equal to the current out. When we look at it that way, it makes a little more sense because it's more of a conservation law where all the charge that comes into a point has to come out. That's where you would get current in is equal to current out. So most of the time I'll be looking at this in this way, which means that I'll express my junction rule in the way that we have in the boxes. The other rule that's going to help us figure out how much current is going in these different branches of a circuit is called the loop rule. And this has to do with changes as potential as you go around a closed loop. That means that you start where you end. And so as you go from your starting point, you may have places where you have potential rises or positive potential difference. And you also might have places where there's potential losses, which would be negative potential differences. The idea is if you go around the loop, these will actually end up equaling 0. That is, all the rises minus all the drops will be 0. Things get a little bit more confusing when we talk about the loop rule because there's rules for us to figure out whether we are going to get a potential gain or loss as we go through an element in the circuit. Let's start with the simpler case of just looking at the battery. Now, we'll talk about how we go around in a loop. You get to choose. There's lots of freedom in these problems in that you get to choose how you approach them with some guardrails on them. But when you look at a loop, basically the only restriction is you want to begin where you ended. If we go over here, if I start here, imagine if I go through a loop and when I get to the battery, in the direction that I'm traveling for my loop, I actually go from a positive terminal of the battery to the negative. That actually would be a potential loss. So I would write that as minus the EMF of the battery. So if it's like 12 volts, I will put minus 12. Here, when we look at the other case What if I go through a battery and I'm going from negative to positive? That actually will give me a potential gain. So then I'll have a plus 12 volts if that is the EMF of the battery. So batteries are basically positive or negative depending on whether you're going around from the positive terminal to the negative terminal, which gives you a negative voltage change. Or if you go from negative to positive terminal, you get a potential gain positive. Then the only other thing we need to worry about is going through a resistor. If we go through a resistor, we have already chosen the direction of the current for that particular resistor. And when I do an example, I think this will make more sense. But if we travel through the loop and go through the resistor opposite the direction of the current that we've chosen, we actually get a potential gain of current times resistance. If I go through the resistor in the direction of the current that I've chosen, I actually have a potential loss. So I write these as either a minus current times resistance if it's a loss, or a plus current times resistance if it was a gain. Here's one of those pictures that you know I like. It's showing the sum of potential rises and losses as I go around a loop using Kirchhoff's rules. And it even allows me to draw this picture when I have more than one battery, because it still is going to end up bringing me back to where I started. So if I started up here, right after I went through the battery, I lose potential through the two resistors, and then I'll travel through each battery. Oh, there's another resistor, so I lose a little bit there, and then I gain finally through the last battery, and I end up where I started. So I like to think about that there's very definite steps that we can follow to do these problems. I think sometimes you will gravitate towards having specific examples or instructions. And so let's just talk about what they are. When you're confronted by a circuit that you need to use these loop rules, the first thing you need to do is to find all the branches where the current could have a different value. Keep in mind it can change every time you hit one of those junction points. So once you've figured out how many different currents you have, you want to label the current in your different branches. And all I mean is I1, I2, I3. Choose your direction. It honestly doesn't matter. I tend to not even think about it, because if you choose the wrong direction, but you do your algebra right, you will just get the answer, but it'll be negative. And all that means is the direction you chose for that current was incorrect, and it goes in the opposite direction. It will not affect your ability to get the answer right. So once you've chosen your direction of your currents, use the junction rule to see how the currents that come into a junction relate to the currents that come out. So that'll be one equation. Then you find loops that you can follow in the circuit. Usually, there'll just be two loops. So those are equations 2 and 3. And you use the rules that we just talked about for potential gains and losses to go around the loop, and you write the equation you get. Knowing how many loops you need will be sort of ruled by how many unknowns you have, which are usually the currents that are traveling in different branches. If you have 3 unknown currents, you will need 3 equations. And this is what I kind of wrote for here. 2 are loops and 1 is the junction rule. That's usually the type of problems we have, because if you get more, the algebra gets super messy. And that is what you do for the last step, is use your algebra skills to solve for your unknowns. I'm going to do this example, and we'll talk about, I think once we see it being used, it'll make a lot more sense. I have 2 junction points on this circuit, and that means there's a certain amount of current that goes through this side, there's a certain amount that goes through the middle, and then there's a certain amount of current that goes through the right-hand side. I'm going to have 3 different values of current. I'm just going to write them down, label them, not going to worry about it, because I know that if I get the answer, if I got the direction wrong, I will just get a negative value. So I'm going to say that this is I1 through the left-hand side. I'm going to call this I2. And then I'm going to call this I3. I'm going to use this junction point to relate my currents. The currents coming in are I1 and I3, and the current coming out is I2. So that is one equation. Now I have to do loop rules. And again, I don't spend a lot of time thinking about the loops, although I have a personal preference of liking to go through the battery from negative to positive, so that's a positive delta V. So this is loop 1. I'm going to start at the battery, and I'm going to have a positive potential difference of 12 volts. Then I go through R1. I'm going in the same direction as the current, so that's a loss, and it's I1 times R1. Then I go down through the middle. I'm going with the current again. This time the current's I2, and the resistor's R2. I'm just going to put in the values for the resistance. So that is my second equation that I can use. Now I'm going to do a loop on the other side. I'm going to go around like this and call it loop 2. Again, I used my personal preference of liking to go through the battery from negative to positive, so I get a positive potential difference. So I come out of there, I go around, nothing happens till I go down through the middle. I go through resistor 2 with current 2, so that's a loss. And then I'm going to go through resistor 3 with the current, but that's I3. And now I'm going to substitute the values for the resistor. So these are my 3 equations that I can use to solve for my unknowns. The thing is I want them to both be, I want these 2 to be in the same 2 currents. This one's in terms of I1 and I2, but this one's in terms of I2 and I3. So I want to either get rid of I1 in loop 1, in this one, or I want to get rid of I3 here. I'm going to rearrange and say I3 is I2 minus I1, and I'm going to take this and substitute it in here. So I have 8 minus 3i2 minus 2i2 minus I1. 8 minus 3i2 minus 2i2 plus 2i1. So this will be my new second equation. So I have 8 plus 2i1 minus 5i2. And the other equation was 12 minus 4i1 minus 3i2 equals 0. I usually like to multiply one of my equations by a constant and then add the equations or subtract them so that I can get down to one unknown. And the idea is to get one of the sets of coefficients to have the same value. So I notice if I multiply the top equation by 2, then the coefficient of I1 will be 4 in both the top equation and the bottom one. So I'm going to do that here. I get 16 plus 4i1 minus 10i2. So my first equation's been modified. The second one remains the same. And now I'm just going to add these two, because when I do, these guys are going to cancel. I get 28 minus 13i2 equals 0. 28 equals 13i2. I2 is 28 over 13. So it's going to be 2 point something. Turned out to be positive, so I was correct about the direction. What I would do is then I would go and I could substitute this into either one of these two equations and get I1. And then finally, I could get I3 by using this equation. Hopefully seeing this done is helpful to see how we would approach this. All right, the last thing we're going to cover in our unit on current will be RC circuits. These are circuits where the current actually depends on time. So the ones that we've done so far, the current had a single value. But in RC circuits, the values can change over time. So we're going to look at these. Basically, when we're talking about an RC circuit, we're either going to be charging that capacitor, because R stands for resistor and C stands for capacitor. So the RC circuit, the two things we might be doing are either charging a capacitor or discharging a capacitor. If we charge the capacitor, we need a battery. If we discharge a capacitor, we don't need a battery. So I like this picture because this provides a picture of a circuit that has a switch where it can either be closed in the position A or position B. And which one it is closed to will determine what we can do. If we close the circuit to position A, what we do is we eliminate this part of the circuit because there's nowhere for the current to go. And now we have a battery, a resistor, and a capacitor. The battery will charge up the capacitor until the capacitor has a voltage equal to that of the battery. Here is a case where I said that sometimes you might see the voltage of the battery written as a script E. This just stands for the EMF voltage. If the switch is closed at point B, we eliminate the battery and we only have a capacitor and a resistor. And this is then what we are doing when we discharge a battery. So when we see the expressions for charging and discharging a capacitor, while I think I have a video where I go through the math, it's not necessary that you are able to do that. We will rely on just the final expressions, but it is important that you recognize which is which, and so understanding the behavior overall of either charging a capacitor or discharging a capacitor is really important. So in this picture, we're trying to show what happens in different times. So when the switch is open, there is no current flowing. We assume we start with an uncharged capacitor, so its potential difference is 0. So Q is equal to 0. Once we close the switch, let's just make this immediately. If this is immediately after we close the switch, that instant that it's closed, the delta V is still 0 of the capacitor, and the potential difference across the resistor is equal to the EMF of the battery. And that means then the current initially is equal to the EMF of the battery over the resistance, which sometimes is written like this. That will be what happens that instant it's closed. But as the capacitor charges, the potential difference across the capacitor will grow, but then also that means the potential difference across the resistor will go down, which also means that the current in the circuit will decrease. The reason that this is because the potential difference across the resistor and the capacitor will always be equal to that of the battery. So it's one of those cases where it adds up to be a certain value, which is the EMF of the battery. But as the potential of the capacitor gets bigger, the potential of the resistor has to get smaller, so they still add up to be the same value. So I already went through this. Okay, so it turns out that we can think about this. It creates what we would call a differential equation, which we can solve to both find the charge as a function of time and the current as a function of time. I want you to look at these expressions and also understand how they correspond to the graphs here. What happens with the charge is it gradually gets bigger and bigger until it reaches or really approaches its final value. So the maximum V across the capacitor is the EMF of the battery. So the maximum charge is C times E, or just big Q. As time gets bigger and bigger, this value will get smaller and smaller, and our charge will approach its final value. you notice that in the denominator here of this exponential, we have r times c. R times c is often called tau, or the time constant. It will actually be able to allow us to quantify how quickly the capacitor will charge up. A bigger time constant would mean longer. The units of tau are actually seconds. The expression for current, which we can actually get from taking the derivative of the charge with respect to time, is this, where it starts at a maximum value and then decreases as time goes on until it reaches zero, which it would do when the capacitor is fully charged. Now, we do the opposite. If we do the discharging of the capacitor starts fully charged. We could call that Q naught. And the instant that we connect it to a resistor, it will start to discharge. And as it discharges, the potential across the capacitor will decrease. And the current, this is where it gets confusing. The magnitude of the current decreases, but it is given a negative value. So technically it becomes less negative. So it kind of increases. It's a little wonky. But basically, what happens is the biggest magnitude of current happens when the switch is just closed, and it'll approach zero, which will mean that the capacitors become fully discharged. These are the expressions for current and charge for a discharging capacitor. This one is maybe more easy to recognize. That is just something that's exponentially falling off. Here, tau is still equal to the resistance times the capacitance. And here's what I said. Because the current flows in the opposite direction when the capacitor is charging up and when it's discharging, we choose to say when it's discharging is that when the current is negative. It does have an initial magnitude of E over R. Remember, this is the EMF of the battery, which is how the capacitor was initially charged. So here's an example of a problem we might have. We have a capacitor of 4.6 microfarads. It has a resistor of 75 kiloohms and an EMF or battery of 245 volts. For the time constant of the circuit, remember that's resistance times capacitance. So, I did the calculations, multiplying resistance times capacitance. We get a time constant of 0.345 seconds. The second question asks how long will it take to charge the capacitor to 1/2 of its maximum charge. This is the maximum charge, and I want this to be Q over 2. You might think you have to calculate the maximum charge, which is equal to C times the EMF of the battery, but we actually don't. We can let this be Q over 2, and then Q, 1 minus E to the minus T over RC. I divide by Q, I get 1/2 equals 1 minus E to the minus T over RC. I'm going to switch sides. Get E to the minus T over RC equals 1/2. And then what I'm going to do is I'm going to take the natural log of both sides. The natural log of the left-hand side gives me the exponent, and this is just the natural log of 1/2. Which is equal to minus 0.6931. So T is equal to minus 0.6931 times RC, which is 0.345. And so our time, it would take 0.239 seconds. And finally, so if solving these types of expressions, when you have the natural log, this E, you might want to review that because you will have to do that if you have one of these problems, which is the second learning objective. And then finally, the current through the circuit at this time, well, we'll just plug into this expression. EMF is 245, resistance is 75 times 10 to the third. E to the minus 0.239 divided by 0.345. And when I saw that, I got a current of 0.0016 amps. Alright, so I hope that you find this helpful. We will spend a little bit of time looking at some of these things on Thursday. And hopefully if you've listened to this video, you understand why I wasn't there today.